This is, so we're talking about gravitational, focusing on, this is the fine-grained streams in the solar neighborhood. This work actually would, has been done by Konstantin over here, myself and Andreas, but most importantly also like from Mark Vogelsberger, who guided pretty much our starting point on the discussion here and like for the fine-grained streams as a cosmologist. So this is my one kind of a slide. It's more like a pedagogical to give you a sense of where everything fits in. So dark matter rate, like if you think about it, the radon detectors will depend on something related to the cross sections typically, and you find in particle physics. But also like there's also depends on the this distribution function, which one of them is the density of the dark matter in the galaxy, and also like it depends on the velocity distribution of the dark matter in the galaxy. So this whole thing is obviously like those are calculated pretty well, but one of the things is that the, cosmology can put input into the rates is the fact that what are these exactly, and the most standard. The standard halo model basically assumes that that goes as 1/r squared for the density of the dark matter, and then it's a Maxwellian velocity profile. So this has been the dominant way that things have been taken into account. So, however, even amongst many people, it's known that that's not quite true, because the dark matter at the last scattering is known to have some very low dispersion. And those dispersion velocities are of the order of 10 to minus 10 C for WIMPs, and then 10 to minus 17 for the Axions. So, so those are well known. And then as a result of some work that Mark Vogelsberger and Simon White did, the idea is they came up with the idea that actually the dark matter distribution anywhere is actually given a superposition of many fine-grained streams, where each of them contributes a certain amount of density of the dark matter. And then the summation of those actually gives rise to what's known as the nominal density of dark matter at a particular location. So, so the question then is that, is there a way then one can tell apart like what that, whether it's a Maxwellian or some coming from this more sophisticated models? In terms of cosmology, also I should point out is that it's still very, very complicated to do calculations to the resolutions that we need for detectors. So meaning the size smaller than meaning the size of the Earth, basically, because our detectors, because you know, the resolutions of these cosmological scales are not quite there yet in that order. So now it's just a bit matter like almost like a chicken and an egg, meaning that in a community of detectors, we like to figure out and then see if we can get feedback into the cosmology and vice versa idea. So what's the abundance of these fine-grained streams? I should also point out here, because these are fine-grained, meaning that that's uniqueness is, and then the low dispersion. Because I want to distinguish those from what's called the tidal streams, which the community might be aware of. Those are much wider dispersion, and the tidal streams come as a result of some halos, sort of because they have a manifestation of that nature. So this is distinguishing for those in community that are aware of the other tidal streams, for instance. Okay, so you know, this is like a graph and a table here that basically gives you an idea of the abundance. So just in this example here, for instance, we have about, let's say, from estimations that Mark and Simon did, it was like we have about 2 million fine-grained streams in the solar neighborhood, and their average density is about 10 to the negative 7, the nominal density. And the probability that one such stream exists in this is actually 100%. So that gives you an idea that you know, we're very, very likely those streams exist in our solar neighborhood. So we can construct a variety of like density scenarios here, and then number of streams. As one can see here from the table, it's finding a stream that has exactly the density of the whole dark matter, it's very unlikely, but you know, it just, the calculations are there. Okay, so then what do we do with this stream? So the idea is that to simulate these streams and then bring them into the solar neighborhood, like meaning the sun and the earth, and then see what happens, whether some relevance to detection. That's the idea. Because it's called dark matter, the nice thing is that it's guided by Newton's law, so it's kind of a little easier in that sense. And one of the things is that some patchwork has been done in the past in terms of like trying to get the sun separate or the earth separate or some of that, but putting it together in a simulation, this is sort of bringing it, and also like putting the fact that the actual there's a particular configuration that solar system has on the galaxies that needs to be accounted for, because that brings kinematical constraints into what comes to the Earth. Okay, so we use this use a simulation basically. Just that's outside solar bodies. That's inside solar bodies. That means it could be the sun and the Earth here in this case. And then we propagate those. The whole thing is done in Python. So. This is an illustration of schematics of you know, the ecliptic plane of the Earth here, and then as the sun is hurled into a Cygnus, and then you could have a scenario like, say, a stream. But obviously, even at 1 astronomical unit, the stream will have the sun will have quite an effect on it, so it needs to be accounted for. But then the stream goes through the Earth. And then, as illustrated here, you can see a density enhancement possibly produced some distance away from the Earth. Just like whenever you do any simulations, obviously you got to figure out that the benchmark plots, that it's working basically by comparing it. This is a graph that this is not necessarily anything new, but it's a way to tell us that the simulations are working. Shows basically that there's sort of like a preferential arrival of the dark matter particles from the Cygnus. I mean, that has to do with the fact that obviously the sun is hurling around the Cygnus, which is you know, known as a dark matter wind. So just a way to illustrate the fact that the simulation benchmark plot shows that that's the case. And then what we do is that now, this has been a very big discussion for us, is like how should we simulate the stream? So obviously they have to have a particular phase space, and what do people in cosmology think that should be the case? And because of the low dispersion, obviously the low dispersion will have to introduce delta functions, which are very narrow Gaussian functions. But the majority of people still think that the Maxwellian velocity profile is sort of the accepted form. However, there's some in the community that thinks that there's a co-rotating disk, just like analogous to the fact that we have a disk that like a regular disk, baryonic disk, that might be the case. To generalize the simulations, in other words, I've included that as a fraction. So you could have up to you can have a co-rotating disk presence, or you can have like fully standard halo model. Okay, but then what happens? You take this big distribution and then you sample the particles from one stream using this basically approximate delta functions, and then you choose basically what comes into the input. And then you figure out at the output, like under the subject to the Newtonian physics, and then figure out what happens at the output, and then also observationally. And this is the distribution functions for different particles. This is assuming a pure SHM model, and this is assuming a co-rotating disk. By the way, that 0.32 is not. It's taken by some authors that believe that that's the number. So it's not. It's just not you know, obviously just to give some numbers that are a little more meaningful with the literature. So this shows like so after accounting the sun, and this shows like simulates several particles here as they come. They go through the Earth, and then obviously you can see this gravitational focus in here, and then let's zoom in under that, and then we define this region as sort of like as a high density region, and then because then we can figure out that what is the density compared to the unperturbed from the gravity case, and this is sort of another view of it, but as you see, like right in the central region, like away from you have a very high density regions produced by the streams, and then. So it shows from two variety of angles here, and this shows what's called the amplification as a function of distance over radii of the Earth. So in other words, where do they form? How far away do they form? Okay, so first of all, what is the amplification? Basically, Liouville's theorem gives you an idea how the phase space evolves, and then knowing the fact that the velocity is approximately the same before and after gravity around the Earth, basically before and after, then we can calculate this ratio. This ratio of those two, that's two basically areas. S sub f stands for the area like at the focus, and S0 stands for the area before the gravitational focusing. And then we can calculate this amplification factor here. The amplification factors are locations where this density enhancements are very dependent on velocity. So the Earth is a velocity selector, in other words. But the peaks, the maximum peaks, are nearly independent of velocity. So one can achieve peaks, dispersionless streams of about 10 to the 9. So that's a very high amplification factors. And but in order to get from amplification into a density, we got to do some calculation. In multi-stream environment, it gets complicated because you got to do all the streams, but there are certain regions that are dominated by a single stream because the Earth is acts as a velocity selector for the streams. Then in those cases, we can calculate the density using the density of one stream before focusing multiplied by the amplification factor to figure out the density now afterwards. So then this is this defines like a width and a length for the region here, and these regions, by the way, are not necessarily with constant density. But what I do is that in order to kind of give a breadth of ideas, is that I use some sort of like what I call an amplification average. What does that mean? Is that the smaller the amplification average, that means that I'm considering a wider region of consideration or region of interest, and then. The velocity, also from the point of view of observations, a lot of things are far away, far out of reach, because obviously at most things we have are around the Earth. So I consider two scenarios here. One is at 1 radii. Obviously most of the detectors on the Earth are at the surface of the Earth. And then one of them is 5 Earth radii. That's to consider like satellite experiments that are pretty much all around. And then obviously by putting those, that imposes a cut in the simulation on what velocities are accepted. And then what's also like consider the fact that dispersion. What's the role of dispersion on the application? So here basically for axions is almost the same as dispersionless streams, so no effect for axions. WIMPs drop a factor of 10. So the WIMPs, our amplification drops by a factor of 10. And then also like as a benchmark plot, you see these green plots that look pretty much all over the place. Those are Maxwellian. So basically shows that if the scenario is fully Maxwellian picture, there's no amplification to be had whatsoever. There's nothing which is to be expected. Only in a stream environment one would be able to see these amplification factors. Okay, so these plots are look a little busy with so many pieces, but I just want to clarify a few things here. So first of all, this stands for the y-axis stands for the number of streams that have a density enhancement. In this case, within radius of one Earth radii. So if you have let's analyze, for instance, this graph here. If you have a 4 pi detector on the Earth, basically, then and then you focus on let's say right here, right there, that stands for, you'll have at that point, not all the streams obviously well, only a few of the streams out of all of them will be right close enough to have low enough speed to actually be constrained in the one Earth radii. So here, for instance, you have a few streams. A 4-pi detector should be able to see like few streams or few density enhancement here, at least a factor of 10 times rho 0. Okay, so that's what that graph here. Now, if you move within the same graph, the reason why it changes is because, like I said, the amplification factors are from a small amplification factors to higher amplification factors. So the only thing that changes within one graph is the amplification factor. However, if you jump from one to the next, what changes there is the stream abundance. You know, so because we don't know all of this, so a graph like this will actually give us an idea. Now, it's very sensitive to what kind of model we accept. If it's SHM model, then you have kind of this abundance, but you see like it goes almost a factor of 10 more if one considers like even some co-rotating models. And then we look at the same graph now for the, if you consider 5 Earth radii. So 5 Earth radii, again, to consider satellites and measurement like that. So here in this case, you can have 10 to the 3 streams with density of 10 rho 0 if they're made of axions. There'll be quite a range of streams of density enhancements in within 5 Earth radii. And then you have, if this model is correct, then you have also 10 to the 4th, if that's the case here. Okay, but also want to point out is that in order to see the higher density ones, those are not necessarily excluded. I mean, those are like just simply probabilistically are lower. But again, the whole parameter space need to be searched for because we don't know which one, what kind of streams do we actually have. So therefore, these plots basically are subject to sort of like a research on the parameter space here. Okay, so, but as I mentioned here, is like if you have a 4-pi detector, this is what you should see. So if you can see the whole Earth, basically, that's what you should see. But obviously, none has like this 4-pi detector. So the detectors are obviously located in certain places. What's important also from the point of view of streams is that whether do they arrive with some preferential direction in the sky or not. So if they're sampled from Maxwellian, if you consider all streams, they do arrive preferential direction because of Cygnus, just like I said before, and then they'll have this density enhancements on the opposite side to Cygnus, basically. So that's what you see in the 2 top plots if you consider all streams. But from the point of view of detection, we don't see all of them. Most of them are out of reach. Okay, so point of view of detection, these 2 are the ones within the proximity of the Earth, and these 2 are pretty uniform. So from a point of view of arrival direction, nobody anywhere is preferentially has a better location than somebody else in another location. So it's all uniform. And that's because the gravity of the sun primarily scrambles the initial directions of the streams. And then, so we need to consider this fact, and then we go and figure out from one single, like one single detector, what's it like for one single detector. We have, first of all, we calculate number of these high density regions per day, which is calculated this way. This way works as long as the stream arrival is uniform, which is the case here, well, for low density. And then we calculate here, again, that's for an observation of radius of RE. And then that's the axions, that's the WIMPs. And then, for instance here, just to understand it like this graph, so if you have this 2 here, this is for the SHM model, that's for the SHM plus the dark disk model. So you have about 0.02 for axions with density of 10 rho 0, if this is the model, and then 0.005 for axions with density of 10 rho 0 for SHM. But remember, this is only one detector, and it does, like just one sensor. That's what you will see. But obviously, you will scale with the number of detectors linearly in principle here. So this shows you like the time, because it's going to be shown up as a transient signal, primarily because the stream locations this density enhancements will be in a certain location, but as the Earth rotates, meaning the sensor or the detector rotates, it will sort of sweep through those high density regions, and then it will be a transient signal. Okay, so the transient signals here, this is a simple equation to calculate those transient times. Will those transit time go from 1 second to about 10 seconds. So those are our typical times here for the transient signal from the point of view of detection. And then this is the same thing, but done at 5 Earth radii. And then again here we see that the abundance is a little more in this case, but again it's like but that will also mean we got to include instruments like satellites and stuff on space too, not just the earthbound detectors in a scenario like that. So this kind of graph again will provide like a sort of a way parameter space to be searched for. On summary on streams here, like I just want to say that the Earth and the Sun affect the primordial fine-grained streams, and then the Sun scrambles the direction of that. But the Earth itself produces high-density regions, and then these high-density regions were very sensitive to the velocity dispersion, meaning that even for WIMPs, it was like reduced by a factor of 10. But the moment that a fully Maxwellian shows up, it's already, those amplificational gains are gone, basically. And it's possible to parse the parameter space and discriminate between the isothermal model, which is and then also the models that include fine-grained stream nature. So in other words, any kind of search is motivated by cosmology in this case, because we can parse into that parameter space and then also single out whether this fine-grained stream nature is the fact, or is it like a little more isothermal. And a network of detectors looking for transient signal is the ideal way to search, because the network will be located in a variety of locations. So in other words, it doesn't look like it matters which locations are preferential, but it will look, and we will be everywhere. And then also we'll look for these transient signals. So basically these high density regions can be searched in this way, and the larger the network, the better the chances of seeing them. So in a way, like this is the ideal way to search for them. And then also, like, by the way, we have some parallel work here. I'm not quite done with the talk. We have a couple slides with another work we've been doing with Ariel Azra. And this is actually, we're taking this idea of streams and then put it into what's called the echo method. Okay, so the idea is that we want to search for what's the parameter space looks like if this fine-grained stream nature is true. And then, in this idea, there's a simulated axion decay into photons. This is with this occupancy number, then the actual axion lifetime drops because we have very high suppression factors here. And then what is the process? What's the idea behind the echo method? The echo method, basically, you send radio waves into a certain region, and if they encounter some density regions of dark matter or axions, then you have this an echo reflected photon, and the other one goes back to back, and then that echo we can calculate this power. And here's some calculations if this isothermal model is the case. And then we go in and then we took this, and what if the stream nature is the case? And then we go in here is that it was there because for the stream nature we need to know basically how far away can one probe here with this echo method. But this is determined by this variable d max. And that kind of shows, so we basically recalculated simulations to actually figure out what those maximum values are. And then that limits basically how far away we can probe. And then since in the radio waves we can go quite a bit far because it's transparent, then means that we're not necessarily limited by the atmosphere. And then these are two important graphs that are basically is that if the isothermal model is true, then by the way, there's the green and then there's a blue here. We're taking those for two particular radio telescopes. One is the Green Banks telescope, and the other one is the square kilometer array. So if the isothermal model is true, that's those two. So those are the two. But if the stream model is true, and then you can probe a much deeper parameter space. You can probe like a much more. So this is only probing without gravitational focusing. This is the same thing with gravitational focusing. So the parameter space being probed here is much larger. And then this plots the uncertainty on the shaded area. It has to do with the fact that we do not know exactly the stream location. So we got to consider range here. So that's it. I'll leave it at thank you.
Thank you very much for this very interesting talk, and we have time for questions. Yes.
Sorry, there was a point where you had a variable, which I'm not sure I understood. The rho s is the percentage of dark matter that is in streams. There was the point where you had a bunch of plots.
Yeah, the rho s is how much dark matter one single stream carries. So one single is that
Can you go back to the plot maybe? Here you have rho s, maybe I'm just not reading it correctly. Rho s equals 10 to the minus 2 rho naught. That's the dotted blue line, right? And what is this rho s here? That's
rho s is like if one stream carries, let's say if we pick this one for instance, where it says rho s is 10 to negative 7 rho 0, that means one single stream of that carries like 10 to the negative 7 of the total dark matter density. So only one, but not all of them are together, correct? Because for this kind of type, we have about 2 million streams. But each of them carries about 10 to negative 7 rho 0.
And is rho s a free parameter? Do you know to determine rho s from simulations or?
Yeah, simulations, that's right. Yeah, from the cosmological simulations.
So how much total is within the streams?
Yeah, you could, maybe one way to say, like in the summary, more than 2 million streams carry half the dark matter density, basically. And then there's 10 to the 12 streams in the solar neighborhood, roughly, but only 2 million of them carry half the density because they're the densest ones, correct? So the rest of them are to basically carry so little of that, but they're more numerous. So they're more numerous because they don't have as much density.
Another question over there.
Thanks for an interesting talk. I have a question about this, precisely this, and the starting point with the simulations by White and Vogelsberg. So you include baryonic effects, obviously, in what you're doing now with the focusing and the lens, etc. Yeah. Do the simulations by Vogelsberg and White include baryonic effects, and do they account for uncertainties in the baryonic effects in determining the distribution of the streams?
Yeah, they do have some account of baryonic effects, but however, it doesn't come up eventually for us to know whether this co-moving disk is it's not enough to know whether we do have a co-moving disk with the baryonic effects or not. So yeah, but yeah, they're considered part of the simulations. Yeah.
Rho dark disk that you've taken as 32% of rho naught, that strikes me as quite a large sort of fraction. What's the scale height and the total percentage of the dark matter of the dark matter of the galaxy that you assume to be in the dark disk?
Yeah, so there'll be about 30. So if the dark disk, then in that case, I guess there'll be 30% will come from that. But again, this is from a paper that already put that. It's not necessarily like to say that that's the true. It's just a way to give a range of,
right.
And then to allow the model to account for those kinds of things.
But we would be inside the dark disk, so you wouldn't be able to have 32% of the galactic dark matter in a dark disk. Actually, there's a strong sort of upper limit on that from Gaia, which says that less than 1% of galactic dark matter could be in a dark disk.
Oh, 1%?
Less than 1%, yeah.
Less than 1%, okay. Well, yeah, thank you. Yeah, like that's again, it's just only to consider the range there.
What's the justification behind this velocity dispersions that you chose for the
behind which one?
The velocity dispersions, these extremely small velocity dispersions.
Yeah, it's just because of the like at the last scattering, still the dark. It's from a 6-dimensional, it's only 3-dimensional, so you have a very low dispersion for the primordial streams. But like for instance the tidal streams, then there will be like you could have multiple primordial streams kind of coming together and forming a tidal stream.
But that's at formation. The velocity dispersion will grow over time as the forms.
Okay. So you're bringing a good question. Whether do we know for sure, like whether as time goes on, because as the dark matter goes around the galaxy, it will start sort of accruing some larger value for dispersion.
Yeah, they'll sort of puff up as they fall into the halo, I think.
Yeah. So I mean I don't like I'm not like on the simulation of cosmology that much, but I mean you got to start somewhere, and then we kind of, as we know better, then we kind of we do improve our simulations, I guess.
Thank you.
Yeah, thanks for the interesting talk also. And I think my question is related to Kieran's. I was wondering, I suppose, if as you're focusing the stream behind the Earth or whatever it is, there's a chance of a gravitational back reaction where essentially you're starting to create some structure that's going to stay long term as once the dark matter has been concentrated behind, if that makes sense, and that just seeds small scale dark matter structure formation.
Oh, I see. Okay. Yeah, these are very small. Like we're talking probably at the order of radii of like a few kilometers. Mm-hmm. So if you if it was right here, like you'll span like about a few kilometers, up to 10 kilometers this way. Maybe the height might be about 1/5 of the radii of the Earth. But not. Yeah, it's just too.
I see. So even as it's growing, then over time, that wouldn't increase massively.
No, it's not necessarily growing. It's just you'll stay fixed with respect to the stars, but as the Earth rotates, a detector will sweep through it, like just because as we move around the Earth, but it wouldn't grow necessarily with time.
Okay, thank you.
Let's thank the speaker again.